Hi, everyone. I'm Zhipeng from University of Texas at Austin. Today, I present my work, Boki, Stateful Serverless Computing with shared logs. In today's cloud computing, serverless computing is a popular paradigm. Cloud providers offer function service, or FaaS. The user simply invoke their cloud functions that execute on cloud provider's infrastructure. If the functions are stateless, FaaS is easy to use and highly elastic. They can easily support thousands of concurrent functions. However, storage becomes more complicated when functions are stateful. Cloud providers offer various kinds of storage services for serverless functions to store their state. For stateful functions running on FaaS, they interact with these external storage services for maintaining their state. In reality, service applications often compose multiple functions, for example, service workflows. This function can concurrently access and update state maintaining other external storage services. Also, each function can fail during their execution, potentially leaving inconsistent state stored in database. So that in general, state consistency with fault tolerance is actually very difficult in the current infrastructure. Let's go over an example. Consider we have a conference registration app built with a serverless workflow. Suppose I'm going to register for SOSP with this app. It first has a function X for creating a profile for me. It first generates a new person ID for me by using read and incremental operations with the database. Then it writes my name to the profile table with the user ID as a key. The function X invokes another function Y, which is responsible for adding my user ID to the attendance list of the conference. Function Y is invoked with user ID, and it makes an append list update with the conference table to the database. However, failures can happen in different places. For example, it can happen within function X in between two database statements. It can also happen when invoking function Y. In this case, function Y may not be invoked successfully. In both cases, data stored in the cloud database can be inconsistent. For example, the profile is created, but the attendance list is not updated. When failure happens, the workflow is restored, and there's no easy way to detect and fix the problem. A common solution for this kind of problem is a log-based mechanism for fault tolerance. For example, write-head logging. The shared log can actually be used as a storage media for the write-head log. In this approach, all operations are logged before executed, including database statements, and also invoking another functions. So with such a log, when failure happens, the workflow can inspect the log to understand its progress and respond accordingly. For example, redo unfinished operations and skip finished operations. Besides write-head logging, we actually can have another serverless use pattern of shared log. Consider applications consisting concurrently running functions and how to maintain a shared state between them. We have a classical wisdom state machine replication and distributed systems, and the shared log can actually provide the storage media for SMR. In this case, function XYZ, they all append state machine commands to the shared log. They can potentially do this concurrently, and the log will order these commands. Later, function XY, they all read back commands from the log. They will all read the same sequence of commands. So that shared state machine can be reconstructed by applying the commands in this sequence. We can see in this example, the total order provided by the shared log is actually the source of consistency. So this is our proposed system, Boki, which is a FaaS plus shared logs and support libraries. We start from fast runtime for executing serverless functions. We use Nightcall, one of our previous works. Nightcall is a low latency fast runtime optimizing for microservices. We then add shared logs. These two components compose Boki's underlying runtime. Boki export a LogBook API for serverless functions to use its shared logs. On top of LogBook API, we build support libraries to simplify the usage of shared logs. Serverless functions can choose to link with these support libraries. Let's start with user-facing LogBook API. A logbook is essentially an append-only log. For every record in a logbook, it has a data field. And every log record has a unique monotonic sequence number, they representing the position of the record in the log. Also, each log record can have a set of tags, potentially empty. Tags is used for selective reads. Logbook's read API allowing providing a tag so that this read will only consider records having the given tag. In this sense, records with the same tag will form a logical substring within a logbook, and this feature is very important for specific shared log use cases. In Boki, every function invocation is associated with a logbook. For service applications composing multiple functions, its functions will associate to the same logbook. In this case, the shared logbook can be used for managing states between its functions with consistency and fault tolerance. So now let's dig into Boki's share log. We have many previous excellent designs of share logs, but serverless environments create new challenges for Boki. Specifically, the serverless environment requires Boki to efficiently support diverse use patterns of share logs. We want high throughput because state-of-the-art share log systems can achieve append throughput more than 1 million appends per second. Boki must provide this level of performance for applications requiring it. We want low latency. The serverless environments use disaggregated machines for compute and storage, so that low latency reads can only be achieved by caching data on compute nodes. In this case, Boki has to address the issue of reconsistency. We want high density. In the serverless setup, a large amount of applications will only use a small amount of resource. Boki has to efficiently support high density of small logbooks with minimal metadata overhead for individual logbook. Boki actually includes novel techniques for addressing these new challenges. Boki uses multiplexing to achieve high density. Many logbooks will be multiplexed over a fixed number of internal physical logs, and Boki build log indexes for these physical logs to allow flexible logbook reads. For low latency, Boki co-locates log indexes with function nodes. Boki also build a record cache on function nodes. Finally, Boki has an interesting meta-log design that jointly addresses log ordering with high throughput, reconsistency, giving index and caches. Most importantly, the meta-log bridge different components together as a fault-tolerant distributed system. The last piece in Boki's architecture is support libraries. We built 3 support libraries for 3 different serverless use cases. The first library is BokiFlow, which provides fault-tolerant serverless workflows. BokiFlows allow composing stateful functions to form a workflow while providing strong end-to-end guarantees, for example, exactly once execution semantics. The second library is BokiStore. BokiStore is a transactional object store for stateful functions, which provides objects that are modeled as JSON objects. BokiStore achieves strong consistency and provides transaction supports. The last library is BokiQueue. It provides high throughput message queues for serverless functions. BokiQueue enables message parsing and coordinations between functions. They all leverage well-understood techniques, but still require some adoption to work with the LogBook API. We start the evaluation by microbenchmarks on LogBook operations. LogBooks can actually achieve high throughput. The append throughput can scale to 1.2 million appends per second. And Boki's LogBook also achieve low read latency. In this case, that the local log index is used with a cache hit. The read latency is as low as 120 microseconds. For other cases, the median read latency are generally within 1 millisecond. Then we evaluate how Boki support realistic serverless workloads. We start by comparing BokiFlow with Baldi on serverless workflows. We have 3 comparison targets. The unsafe baseline has no mechanism for fault tolerance, so that state can be inconsistent on the workflow failures. And Baldi uses log-based protocols for fault tolerance. Baldi builds a logging layer over cloud database DynamoDB. BokiFlow leverage Baldi's techniques, but using LogBook as the logging layer. Here are the results of microbenchmarks on Baldi's primitive operations. We can see in all cases, BokiFlow can significantly lower latencies compared to Baldi. This justifies that Boki can actually provide a much more performant logging layer to support Baldi's fault tolerance protocols. Then in the benchmark of realistic workflows, BokiFlow significantly speed up the end-to-end execution time, while providing the same strong guarantee as Baldi. BokiFlow speed up the median execution time by up to 4.7x. We then evaluate BokiQueue. We compare BokiQueue with Amazon Simple Queue service and Apache Pulsar. We test with various setup of producer-consumer functions. For message throughput, in every setup, BokiQueue has higher message throughput. Also, in all the tested setup, BokiQueue has the lowest message delivery latency. Conclusion. Boki justifies the value of share log in stateful serverless, where share logs can provide mechanism for consistency and fault tolerance. Boki proposed novel share log techniques to address unique challenges introduced by the serverless environment. Boki support libraries demonstrate how share log can support 3 different serverless use cases, and evaluation of these libraries shows that Boki can speed up important serverless workloads by up to 4.7x. Finally, Boki is open source on GitHub. Thanks very much for listening.